Hello. We're going to look in now on some slides for section 7-5, estimating a population standard deviation or variance. So in this section, we're going to be using confidence intervals to estimate population standard deviations or variances. So a key concept in this section, we're going to introduce a new distribution, the chi-square probability distribution, so that we can construct confidence interval estimates of a population, standard deviation, or variance. So notice this is a new distribution for new types of confidence intervals, just like how in the last section we introduced the t distribution for confidence intervals estimating population means when the standard deviation of the population was not known. So there are ways you can also estimate needed sample sizes for certain confidence intervals of this nature, but it's a bit overcomplicated of a process, so we're not going to worry about finding sample sizes for these types of confidence intervals. Okay, so the chi-square distribution in a normally distributed population with variance sigma squared. Assume that we randomly select independent samples of size n, and for each sample, compute the sample variance, s squared, which is the square of the sample standard deviation, s. Now, the sample statistic, chi-square, has the sampling distribution called the chi-square distribution. Now, this is just an explanation, kind of telling you like where the chi distribution is coming from. And so you can see by this formula here, where chi-square actually comes from is from the degrees of freedom times sample sample variances, all divided by population variances. But so again, this is just kind of letting you know where all this comes from, but you don't need to dig too much into detail with where all this is coming from for chi-square distributions. We also just want to show you kind of how to use the chi-square distribution for confidence intervals, estimating population means, standard deviations or variances. So some properties of the distribution of the chi-square statistic. The chi-square distribution is not symmetric, and if you look at this picture here, actually it's a bit more skewed right, is how it starts out. And unlike the normal and student t distributions, as the number of degrees of freedom increases, the distribution becomes more symmetric. Notice, for example, this chi-square with the degrees of freedom of 10, and looks pretty skewed right still, and then when you increase the degrees of freedom to 20, it starts to look a bit more symmetric. And another key thing to notice here is also these are both starting at 0, which I'll talk about more in just a bit here. And because the values of chi-square can be 0 or positive, but it cannot be negative, since it's essentially a chi-square number. And say, for example, anytime you square a negative, you're always going to get a positive anyways. Now, the chi-square distribution is different for each number of degrees of freedom, which that degrees of freedom is still just equal to n minus 1. And as the number of degrees of freedom increases, the chi-square distribution approaches a normal distribution, essentially. Hence why I was getting more symmetric. In table A-4, which is in page 607 in your book, each critical value of chi-square corresponds to an area given in the top row of the table, and that area represents the cumulative area located to the right of the critical value. So ultimately, just know that table is where you're going to look for chi-square critical values. I'll show you how to use that in just a bit. So for example here, a simple random sample of 22 IQ scores is obtained. Construction of a confidence interval for the population standard deviation sigma requires the left and right critical values of chi-square, corresponding to a confidence level of 95% and a sample size of n equals 22. So I'm just going to find the critical values corresponding to that. And notice since we have that sample size n, that of course means our degrees of freedom is going to have to be 21. And so this is what that's going to kind of look like. So here's a chi-square distribution for degrees of freedom of 21. Notice our left The critical value here is 10.283, and then our right critical value is 35.479. And both of these have tail values 0.025, just meaning that we've got this middle 95%, again here for a 95% confidence interval. Now, how you find these critical values from the table is like this. This is what the chi-square table looks like in your book. And again, notice it says area to the right of critical values is what it gives us each time. And so what I want to look for first is find the row for the degrees of freedom I want. So 21 here in this row. Now, say I want to find the left critical value first. So to the left of the critical value was 0.025 for the area, or that probability, so which means 0.975 is what will be to the right of it. And so that's where I look down that column and then trace over 21. So I see that my critical value there is just that 10.283. So that's my left critical value. And then now for the right critical value, look in that same column, 0.025, because that's the area to the right of my right critical value. Look over in 21 again, since that's still the degrees of freedom. And I'm going to use 35.479 for that right critical value. So notice I can't just take a right critical value, make it negative, and get the left one, because there's no negative values in the chi-square distribution. And just some things here that I should hopefully be a little review, just sample variance. A squared is the best point estimate of the population variance. In other words, this one is an unbiased estimator. And sometimes you can use the sample standard deviation as a point estimate for the population standard deviation, although it is a slightly biased estimate, just meaning it's not always the best. Here's just a little recap of some of the notation. So sigma for our population standard deviation, sigma squared, population variance. S is what we usually use for sample standard deviation, S squared for that sample variance, and for the sample size, we still use capital E for the margin of error. And now this variable here is now chi-squared sub L, so that's our left critical value using the chi-square, or left-tailed critical value for chi-square. Then we have chi-squared sub R, so that's our right chi-square critical value. Now some requirements for confidence intervals about standard deviation or variance. Again, we still want simple random samples. And now for these confidence intervals, we need to have a normally distributed population. That one we can't get around for these types of confidence intervals. And this is what ultimately the confidence intervals will look like for variance. So notice you've got the degrees of freedom times that sample standard deviation divided by the right-tailed critical value for chi-squared. And then the upper limit is actually still degrees of freedom times standard deviation squared, or the variance of the sample, then divided by the left-tailed critical value from chi-square. And so it might seem a little backwards having the right value over here and the left value over here, but the right value is always going to be a bigger value. Notice these are the same on top in both fractions. So when I divide by a bigger value, that's going to make this overall thing smaller. And when I divide by this smaller value, this overall value here will be bigger than that lower value. And if you want to just go ahead and get a standard deviation confidence interval from there, you can just take the square root of both sides, and that'll give you a confidence interval for the population standard deviation. So just going through the little procedure here, just first we need to verify that all of our required assumptions are satisfied. So just ultimately dealing with a simple random sample and a normal population. And we just make sure we use our degrees of freedom and that chi-square table, using that properly to figure out what our right and left critical values are. Just keep in mind those will be totally different. Then evaluate the upper and lower confidence interval limits. So just kind of plug in everything in that we need to, those critical values that we find, degrees of freedom, and those sample variances. And that'll give us a confidence interval for the population variance That's always where we want to start. And then if we're dealing with a problem that's asking for the confidence interval of a population standard deviation, then just go ahead and take the square root of everything, and that'll finish up your confidence interval. Now we want to lastly round the resulting confidence level limits. If the original set of data to construct a confidence interval, or if we're using the original set of data to construct a confidence interval, rounds the confidence interval limits to one more decimal place than is used for the original set of data. And if you're using the sample standard deviation or variance, round the confidence interval limits to the same number of decimal places. So for example here, suppose a group of 22 subjects took an IQ test during part of a study. Now the subjects had a standard deviation IQ score of 14.3, so that's our sample standard deviation. Then we're going to construct a 95% confidence interval of the population standard deviation there. So we're going to treat this as a simple random sample, and suppose this is a distribution of those 22 IQ scores. Then it looks like that's about normal, roughly. Just one little bit of outlier here, so that's not too bad. So that'll be close enough for normal that we can use this. And so again, just using 21 for our degrees of freedom. Notice we're using the same scenario numbers from before, so we're still using that left critical value of 10.283 and the right critical value of 35.479. Just kind of plugging everything into our formula here. So 22 minus 1, get our degrees of freedom. Plug in 14.3 for that sample standard deviation. We're going to square it. And once we would evaluate everything there, we would find that that confidence interval for the population variance comes out to 121 to 417.6. And if we wanted to find that confidence interval as standard deviation confidence interval, just take the square root of both of those. And so that would put our confidence interval between 11 and 20.4. So in other words, we'd be 95% confident that the population standard deviation is between 11 and 20.4. And let's see, just want to do a little recap with the different distributions that we covered in this chapter. So ultimately, we'll still use the z distribution sometimes and z critical values. Just keep in mind that z table only gives you left areas. And so use those for confidence intervals with population proportions. You also use those for confidence intervals for population means when the population standard deviation is known. You also use the z table or z critical values more for finding sample sizes anytime. Then for the t distribution, just keep in mind that gives you tail areas. So whether you're looking at just one tail or two tails when you're looking at that table. And use that for finding confidence intervals of the population mean when the standard deviation of the population is not known, but hopefully you'll have the sample standard deviation instead. And lastly, in this chapter, we go and use the chi-square distribution for when we're finding confidence intervals of population variances or standard deviations. And keep in mind that table only gives you right areas, and it will have completely different lower and upper critical values each time, or left and right critical values. And I think just last thing here, I just believe I actually misspoke on this confidence interval. Keep in mind that for this confidence interval, we'll be 95% confident that this interval 11 to 20.4, we're 95% confident that it contains the true value of the population standard deviation. All right, then that's the end of chapter 7.